So in this session, what we're going to do is, so this is number 12, what we're going to do is take module 1, the concepts that we saw in the last session, and solve problems related to it. We did see a few in the last session. I think, okay, so they were all only these type of questions. Okay, let's move on then. You can also see a few of the questions from module 1. So we had done module 6 in the last class, so we can see a few questions in module 1 and then we can start solving module 6. This question, let me also paste the figure that is part of the question. Okay, so the question says a computer A sends a message to computer D via so LAN 1, that's labeled A, LAN 1, router 1, R1, LAN 2, that's also labeled. Show the content of the packets and frames at the network and data link here for each hop interface. So make it a little bigger. You have a sender and it's sending a packet all the way along this LAN into the router, from the LAN and back to the sender. The packets that you're going to have in this network, you're going to have a packet over here when in this LAN before it reaches the router, and then the router is going to send another packet. So you're going to have another packet over here. Now we need to find out what are the contents of these packets. What will these packets hold such that this message is going to be transferred? And I'm going to paste the solution of this. Then we can discuss the solution together. So the solution. So what is this? How did we get all these values? So you can see you have a packet, 2 packets, and what you'll notice is they divide into 3 parts. You have an address, you have 2 identifiers, and the data part is the last part. So what is this address that is given? This is actually the address from where the packet is coming. So 42 is actually the address from the LAN, and 40 is an address coming from the host. And together, when they put it, you get 4240. What is A and D? A is identifier for the sender, and D is the identifier for the receiver. And then you have the data. If you're sending a package from here, from D80, what will it be? It will be the same thing. You have the address of the sender, 80, 82 for the LAN, sender and receiver, and the data. So this is just an important question that I want to to discuss. This is actually part of your first module. Um, it involves writing out what packets will be formed in the network. And there's a variation of this problem. Um, Here's another part of the problem. So what does it say? It says in figure 2.22, that's the one that we have here. Assume that communication is between the processes running at computer A with port address I and process D with port address J. Show the contents of packets and frames of the network data link transport layer for each of them. So what is the difference between these two questions? The only difference is they've mentioned port addresses. And we have already determined what the packets will look like. And I've already defined that here. So how will this answer look different from the first one? And it's basically only the ports. So I'll paste that part also. Okay. What do you see? What is the difference between these two? You can see that they've put the sending address, and let me make it bigger. They put the sending address, they put the sender destination identifiers, then they've added the ports. And after the ports, only they put the data. Same thing for this side. You have the address, identifiers, ports, then the data. That is how you will solve this. Okay. Okay. So this was our first question of the day. There's actually one from module one. So the rest of the questions we'll see after this will be continuing from module 6 that we discussed in the previous session yesterday. Question 2. Okay, let's look at this question. So a client uses TCP to send data to a server. Okay, the data is 16 bytes. Calculate the efficiency of this transmission at the TCP level, ratio of useful bytes to total bytes. Calculate the efficiency of transmission at the IP level. Assume no options for the IP header. Calculate the efficiency of the transmission at the data link layer. Assume no options for IF header and use Ethernet at the data link layer. So this question has three parts. So we have to find TCP efficiency, IP efficiency, efficiency, and data link efficiency. These are the three types of efficiency that we'll ask. And they've also given us what is efficiency. What is efficiency? It's given here as ratio of useful bytes to total bytes. So let's write that down also. Efficiency, to, sorry, useful bytes, total bytes. What is this useful bytes and total bytes? We know that when we have a package, we saw in the previous question also, the package is divided into two parts. Have header and you have the data. And so which of these is the useful part? It's the data, right? So data is the one that's going to be having the actual information that needs to be transferred. The reason why we are sending the package. But the header has, what does the header have? It has the destination addresses, the options, those kind of things. So when they say your useful piece to total bytes, they're actually saying, let me change. Useful is the data and total is the data plus the header. That's all that you need to know. So you just need to take data divided by the data plus header. That will be your efficiency. Okay, so let's solve. In the case of TCP efficiency, so let's say solution TCP efficiency. So one thing you should know, so we have everywhere in this question, we have no options, right? It said no options, calculated no options. Everything is in that way. So we need to know what will be the size of a header without any options. So let me give it to you here. With no options, TCP header is only 20 bytes. IP header is the same, 20 bytes. It's the options in the TCP header that makes it more heavier than the IP header. And lastly, Ethernet header. Ethernet header, if it does not have, so why are we doing Ethernet header in data link layer? Because they said use Ethernet and data link. The Ethernet header without any options is 18 bytes. Okay, so now we have this information. How can we use it to solve? TCP efficiency, useful bytes. So let's say useful plus total, useful divided by total, which is equal to data divided by data plus header, which is equal to how much is the data? Data is given as 16 bytes. And how much is the data plus header? 16 plus TCP header 20. That is your answer. What is a 0.44? Or we can write 44% efficiency. Correct? Next, we can move on to the next part. What is asked? IP header, IP efficiency. What is the efficiency in internet protocol? So again, UIT. Again, data by the plus header. So again, 16 divided by 16 and IP header 20, and we'll get 0.044. But this is actually wrong. What is wrong about this? So if you think about it, IP header is in, when you're using an IP header, you're using it on top of a TCP header, right? Because what layer is the TCP protocol in. So the transport layer, what level is the IP protocol? The network layer, when you put them both, when you put them together, they'll actually add up to each other. So the TCP header will still be there when IP header is there. So what is the right way of solving this? It's actually 16 divided by 16 plus 20 plus 20. That is equal to 28 point. So it's equal to 0.2857. So that is equal to 28.57% efficiency. Efficiency. Okay. So now the last part, data link. Again, same thing. Data by data plus header. Now you know header has to include not only the header of that level, but also the previous, all the previous ones. So here it will be equal to 16 by 16 plus 20 plus 20. The first one is for TCP, second one is for IP, and last one is for Ethernet. That will be your value. So this is equal to 21.62% efficiency. Okay. So what I wanted to point out was that this was the wrong way to do it. The right way to do it. So let's recap this question. This question gave us three gave us to calculate what is the efficiency. And they gave us how much data, what's the size of the data, and how many options and what how the options are. So these are no options. Use Ethernet. We find an IP and find an TCP. So the only thing you have to remember if you want to solve this question is this: the header length. Without option, how big is the header? That's the only thing that you need to remember. Okay, let's move. Question 3. Here is a theoretical based question. Question is, an IP datagram is carrying a TCP segment designed for address, and an address is given 130.14.16.17.7.16. The destination post is corrupted and arrives at somewhere else. So here we have another address, but you can see this address and this address is not the same because some corruption has happened in between. Now the question is, how does the TCP react? So this has actually nothing to do with this. You just need to know what happens when TCP detects an error. First of all, how does TCP detect an error? It uses something called checksum. What is checksum? We have already seen in the previous sessions. Checksum, what it does, it calculates the thing for the whole thing, and then on the receiver side, it will add it to the data, and it should give all zeros. This is an easy way to find out whether any bit of the package has been corrupted. So simple answer would be, so now how does TCP react when it gets an error? Does it ignore? So we saw in UDP, if there's an error, it just does not notify anything. It just proceeds, right? But in TCP, segment will be dropped and us and so no acknowledgement will be sent. So if no acknowledgement is sent, the sender will automatically resend this packet and then it will reach the correct destination. It will not get, if it gets corrupted again, then again the sender will need to send, but eventually the packet will get to the correct destination. So the sender will need to, or will be forced to resend the package. Okay, that was this question. You drop in the package and you resend. Okay, let's move on. Then 4. The question is, a TCP connection is using a window size of, so we are given, there is a window and they've given some size also. And then we're given, and the previous acknowledgement number was something. They're given us what? ACK number. It received the segment with acknowledgement number something. So we're given the second time we got an acknowledgement number. It's the first time. And window size of advertisement is 12,000. Draw a diagram to show the situation of the window before and after. So what exactly is happening here? You have two windows. So I'll paste the official diagram, but before that, let's try and understand. So you have a window, and that size of that window is 10,000. This is before, and this is after. You have another window, and the size is 12,000. Now we need to find what is the address of the first and the last. So if we go back to yesterday's session, in TCP, we will find that the the sequence number where it starts is from the acknowledgement. What do I mean? So I don't think, yeah. So anyway, if you have an acknowledgement, let's say from byte 0, byte 1, that means that so if you have an acknowledgement at byte 1, the window will start. That's all that you need to know. Whatever the acknowledgement is, one bit after that, the window will start, right? So what do we have here? The acknowledgement So they already given that number. So they already said where it's starting from. So it is starting from 2200. Where is it ending? So let's do for this. Okay, where will this end? So we know the length of this is 10,000. That means all we have to do is add 10 to the 22,001 or 32,001. That's it. That's the how it looks in the before case. You have a start at 22,001. You have a window length of 10,000, and then it'll end at 32,001. What about the second case? You have a new acknowledgement number at 24,000. What will be the destination? Again, in the same way, all you have to do is add what is the window size? 36,000. Where did the 36,000 go? So where did this 24,000 come? From the question. They said the acknowledgement number is 24,000. Here they said the acknowledgement number was 22,000. And they gave us the sizes, size over here and the 12,000 over here. All we had to do was put it together and we can get the window size. So let me show you the official diagram. It's a little neater. Hmm. Here is the official diagram. So what is it shown here? I have a window. They've marked some point here as 2002 to 22,001. They've drawn a window till here, and then what they've done, they've shifted the window to so the same values 24,001, 36,001. They've really moved it this many sides. So it will not. So across the solution, it's actually 36,000. That's because one is also included in that bit. Right, so it's actually 22,000 to 32,000. But the window size will start one bit after, so it will be 22,001. So this is how they've shown a shift of the window, how the window has slid from its initial position to its final position. And it's become bigger. Why has it become bigger? Why this is 10,000, this is 12,000. Why? Because we have a window state advertisement, which is advertising size of 12,000. So that what is that in this question? We were given window size, we were given the acknowledgement number where to start from, and then we are saying after some time we got an acknowledgement number with another advertisement. What will it look like? So this is what it will look like. Okay. Now we can go to the next. Here we are given following is the dump of a TCP header in hexadecimal form. And then we are asked so many questions. So you're given TCP header, you have this full string. Then you ask what is source, what's destination, sequence, acknowledgement type, window size, all these questions. So let's see what is a TCP header. So I'm going to go back to our previous session where we had discussed TCP header. Here it is. We copy that and bring it here also. So you have to remember that the sizes. So source port is 16, destination port 16, sequence number 32, at 32, and based on that you'll be able to finish. Okay, so let's begin. So We are given here in hexadecimal. How do we know how many hexadecimal numbers, hexadecimal digits is one bit? And I have said before, in hexa, one is 4 bits. Hexadecimal. So if one is 4 bits, how much is 16 bits? So let's write this full address again. 0530060712345671234567854007 FF123456. If 1 is 4 bits, it means 4 digits in hexadecimal, that will be equal to 16. So you don't have to do anything. Source port address is the first 4 digits. So let's make the answer. So what I said, answers source port 0532. Next one, destination port. Destination port, again, same thing. We have 4 numbers that will make 16 bits. 0017. That is your destination. What is the sequence number? So sequence number we have 32. 32. So that means we need 8 hexadecimal digits. So next 8 digits 1, 2, 3, 4, 5, 6, 7, 8. So its last digit is 1. That is the sequence number. Next we asked acknowledgement number. Acknowledgement number also has same size. We are given the size is just 8 zeros. Okay. Now we ask what is the length of the header, type of the header, and window size. That is where these come. Window size is the last 16 bits. So before we get to that, so we can actually, so this is 32 bits. But that if you divide by 2, this is 16, this is 16. But we'll come to that. Length of the header is always given by the first digit. So it's represented by 1 digit in hexadecimal. So what is that 1 digit? 5. So these are actually all in hex. And the remaining type represented by these reserved and flag, how much is it? Is going to be the remaining part of that 16 digit thing. That is equal to here it is, so type, here it is O2. And finally, what is window size? What is window size? It's 16 bits, so that means the last 4 CO7FL. That's all. So what was in this question? We saw that if you are given a dump, you should be able to use the header and find all these answers. The only one thing you have to remember is that one hexadecimal digit is 4 bits. Okay, so in this session we saw TCP, how to map a TCP address to different things. We saw this. This is how to practically implement the sliding window if we're given a theoretical concept. Then we saw a theoretical question related to TCP. Then we saw how to calculate efficiency in TCP. And the first question we did today was module 1 question. This is how to draw the packets in a network. Okay, that is all for this session. Next session, what we can do we could continue with a few more questions of module 1, or else we will start with module 7. This is going to be application layer. Okay.